Our speaker today is Ron Garret. He's got a series of talks on the history of science and how we came to our present understanding of how the world works. This installment focuses on astronomy and cosmology, tracing the history of these fields from the ancient Greek thoughts to the recent discoveries of dark matter, dark energy, and gravitational waves. Ron Garret's a software engineer by trade. He's currently working on easy-to-use cryptography software. He was a co-founder and CIO of Virgin Charter, and was an early hire at Google. He was previously a rocket scientist. He also made a feature-length documentary about homelessness. So would you please welcome Ron Garret?
Thank you. Can you hear me? Okay. Thank you all for. Excuse me? Test. Hello.
Ron, is it possible to turn the lights off? We can see the screen better.
You'll have to address that question to somebody else. I don't know.
Yeah. What happened to part one?
Part one was, I gave that a few months ago at the atheist community of San Jose. And there's a video of it on the web somewhere. You'll have to check with them, check with either them or me to get the URL for part one. Thank you all for coming out on a cold, rainy day. I'm really happy to see such a good turnout. So this is a series of talks that about the history of how we came to our present understanding of scientific information, which I think is really important for secular communities to be well versed in, because one of the charges that we get from religious people is that science requires just as much faith as religion, and science is just another kind of religion. And I don't believe that's true. And these talks are designed to be an argument for why that's not true, that we can actually make a much better case for scientific truths than we can for religious truths. This is really the topic that I wanted to start the series with. I started, the first installment was about the history of the atom. And the reason I did it is because it was a follow-on to a talk given by another ACSJ member about how scientists figured out that water was H2O. Which is an interesting story just in and of itself, and is part of the story of how scientists figured out that matter is made of atoms. And so I started with that as sort of an homage to that talk that inspired this whole thing to begin with. But this is really where I think the whole story of scientific history really starts, because it's one of the questions that humans have asked since the dawn of time, is what is our place in the cosmos? And today we have a pretty good answer for that. We're living on a planet that's part of a solar system that's in an obscure little corner of a galaxy that's one of many galaxies that's part of this huge universe that we now have a pretty good picture of. I learned to my surprise that there's at least one member of the audience who's a little skeptical about some of the scientific conventional wisdom about this, and in particular about the Big Bang. And so I now feel the need to ask, is there anyone here who doesn't believe what I just told you? That we're on a planet that revolves around a star that's in a galaxy. Okay, just felt the need to do a little sanity check there. Anyway, so if you were alive, say 5,000 years ago, and you looked up at the sky and saw, well, this, then what I just told you would be far from obvious, even though it's true. And in fact, even today, there are people who are skeptical about what I've just told you. There are actual flat earthers. This is really a thing. There's a substantial community out there. And when I first encountered this, I thought, oh, they're just trolling, kind of like the Church of Satanism. They're really trolls for atheists and rationality. But as far as I can tell, these guys really are serious, and they advance all kinds of actually fairly sophisticated arguments, like this one. I don't really want to spend too much time on this except to tell you that even today, there is a certain amount of controversy about some things that the vast majority of people just take for granted. And so it's handy to be able to debunk these arguments and to know how we know that the Earth is not flat. That's actually fairly easy to debunk. And how we know, for example, that the universe is 13.8 billion years old. That one's a little bit harder to explain, but it's just equally true. So we go back to the beginning to sort of human prehistory and put yourself in the place of one of our ancestors before science was invented, trying to make sense of what you see around you and what can you and think about what that is that you see around you. So what can you see in the sky with your unaided eye? You can see the sun, the moon, the stars, obviously. 5 planets. Anybody know what they are? Mercury, Venus, Mars, Jupiter, and Saturn are the 5 that you can see with your unaided eye. And they look like stars, except they distinguish themselves from the stars in that they move around relative to the stars. All the other stars stay fixed relative to each other. The planets move around. In fact, the name planet comes from the Greek word for wanderer. You can see meteors occasionally, comets, the Milky Way, which you actually can't tell is made of stars if you look at it with your unaided eye. It just looks like... Has everyone here seen the Milky Way with their own eyes? Has anyone not ever seen it? It's actually really hard to see from where we live. Yeah, it's really worthwhile. Go out to the desert where it's dark and see it. It's a breathtaking sight, and the photos of it really don't do it justice. You really ought to make a pilgrimage out to a dark place and see it with your own eyes if you haven't. And then with your unaided eye, you can also see 3 galaxies. You can see a galaxy called M31 here in the northern hemisphere, just barely. If you've got really good eyesight and you kind of look at it sideways, you can just barely make it out. And then there are 2 in the southern hemisphere that are easy to see, called the Magellanic Clouds. And that's it. That's all the data you have if you're an ancient trying to figure out what's going on. And you can also see eclipses. Did anybody here go see the total eclipse recently? Wasn't that cool? The coolest thing to me about it was that it happened right on schedule. I was very fortunate in that I was out in a farmhouse in Idaho, and there was an astronomer there who had this amazing setup. He had a telescope and a computer, and he was counting down the seconds to exactly when totality would hit. And in fact, exactly when he said 3, 2, 1, take your glasses off, that's exactly when it happened, and this was predicted years in advance. And it's just amazing how precise these predictions and accurate these predictions can be. So the ancients could also see eclipses, both lunar and solar eclipses, partial eclipses, total eclipses, and annular eclipses. So that's when the moon is in front of the sun but doesn't block it completely, and there's a ring of sunlight around it. Has anyone here ever seen an annular eclipse? Yeah, those are kind of interesting too. The total eclipses are cooler, but the annular ones they're really interesting. They tell you a lot about they give you a big clue about what's going on, because they tell you that sometimes the moon and the sun are the same size in the sky, and sometimes the moon is a little smaller and it doesn't cover the sun up totally. They also knew about tides, although it's not immediately obvious that tides have anything to do with what's going on up in the sky, except that the timing of tides seems to coincide with how the moon moves around the Earth. And then there's some things about planetary motions that you can observe. For example, you only ever see Mercury and Venus close to the horizon, whereas Mars, Jupiter, and Saturn you see all around. And also Mars does this weird thing called retrograde motion, where all the other planets move in one direction, Saturn and Jupiter are only ever seen to move in one direction. And Mars mostly moves in the same direction, but every now and then it does a little backtrack and goes back in the opposite direction. So one of the things you see is that the physics, the laws that govern the behavior of things up in the sky seem to be very different than the laws that govern the behavior of things down here on Earth. The Earth is chaotic and messy and dirty and base, and the heavens seem to be orderly and pure and clean and divine. And in particular, if you take something here on Earth and you drop and you let go of it, it's going to fall. Whereas the stuff in the sky, it somehow manages to stay up there and never falls, except for meteors. They sometimes fall down. And so you can kind of scratch your head about that. But for the most part, things stay up there. And so you could quite reasonably come to the conclusion that the laws of physics that govern what's up in the sky are different from the laws of physics that govern what's down here on Earth, and advance a theory something like this, that somehow some supernatural force created all this, and that the supernatural force exists up there in the mysterious heavens where things are much neater and cleaner and orderly than they seem to be here on Earth. And as far as we know, that is pretty much what all of our ancestors thought up until about 2,500 years ago, when the Greeks started to think about, invented mathematics and science and started to think more critically about these things. So the history of science starts with the Greeks about 2,500 years ago. This is kind of the big picture of the story of the scientific discovery of the cosmos. It spans a period of about 2,500 years. And, oh, darn it, I forgot my pointer. Oh, I'll do it this. Yeah, we'll do it this way. And it spans two major periods. So there's the Greeks, which go from about 500 BC to 170 AD, and I'll explain the significance of those dates in a second. And then there's a big gap that is historically called the Dark Ages that ended in 1543. Anybody know what happened in 1543? Yeah, okay, we'll get to that. 1543 is a big red letter day in the history of science. And then the modern science starts there and advances to the present day. And 1687 is a date that every secularist really ought to know, because that's when Newton's Principia was first published. And that's really what unleashed the tide of modern scientific advancement. I'm giving you these dates, not to, I don't want this to be, like a history class where you got to really remember the dates. The point I really want to try to make is that the story I'm about to tell you happens in two chapters, and they're both about 500 years long. And the main take-home message is the contrast between the amount of progress that was made in this 500-year period versus this 500-year period. So we'll start with the Greeks, and again, don't get too hung up about the details. There are probably about a dozen or so Greeks that were really important to the story. I'm going to focus only on 6 of them. Each of them is spaced by about 100 years, so roughly one important development per century in the first 500 years.
But didn't Arabs come up with math?
Who?
Arabs.
No, they didn't invent it. They didn't. So there was a during this period that we in the West call the Dark Ages. The Arab world was the center of scientific and mathematical culture and advancement during that time.
Yeah, can I request that anyone that wants to speak, either you have me move the mic to them because we're trying to record it,
Oh, I'm sorry.
okay, or you repeat the question.
So the question was, didn't the Arabs invent math? And they did invent a lot of math, but not in this period. It was during this period of time. And I'm very fuzzy on that history, and the reason I'm fuzzy about it is because, yes, during this time, the center of scientific and mathematical advancement was in the Arab world, but very little of it came back to the Western world to impact the development of modern science, which is very unfortunate because we probably could have, as a species, figured out a lot of this a lot earlier if we paid attention, if we in the West had paid attention to what was going on in the Arab world at the time. But you have to remember that the dominant political dynamic in the world at that time was the religious tension between the Catholic Church in the West and the Islamic faith in the Arab world. And those two cultures didn't get along very well, and so there wasn't really a lot of opportunities for intellectuals in both cultures to kind of get together for scientific conferences and things like that. And yeah, it's tragic. Anyway, so let's start with the Greeks. So the very first record we have of a human scientist actually getting something right about the cosmos is a fellow named Anaxagoras, who was a contemporary of Pythagoras, who invented the famous Pythagorean theorem. So all this is about the same time that the very earliest mathematics is starting to be invented in the Greek world. There's earlier math in Babylon and figuring out how to count and multiply and add and subtract, but what eventually turns into the basis of modern science starts about 500 BC with Pythagoras and Anaxagoras, who correctly figured out that the moon doesn't make light of its own, it's reflecting light from the sun. He correctly figured out that eclipses are caused by, in the case of solar eclipses, by the moon blocking the light, coming between the sun and the earth and blocking its light. And in the case of lunar eclipses, the earth coming between the sun and the moon and blocking the light.
Why does the picture show up with a globe in its hand?
Well, that's a very good question. So, I'll get to that in just a second. He also figured out that the heavenly bodies correctly identified that they are made of the same stuff that Earth is, which at the time was a very radical idea, because most people at the time thought that the heavens were divine, and so they could not possibly be made of the same material. But he reasoned that every now and then something falls down in the form of a meteorite, and when a meteorite hits the Earth and you look at it, it's just a rock. And so he reasoned that the moon and the planets and the stars and everything else must be rocks too. But he believed the Earth was flat, and this is really interesting, because once you've figured out that the moon is reflecting light from the sun and that the eclipses are caused by the interposition of these bodies in between each other, there's a lot of evidence. Once you accept that, there's a lot of evidence that the Earth is round, and in particular, the shadow of the Earth on the moon during an eclipse is round. And nobody really knows why he didn't make that conclusion. It's not evident from his writings. And in fact, there's a whole nother installment of this series that I want to give about history. How do we know what we know about history? Because we don't have any original writings from Anaxagoras. Everything that we know about Anaxagoras is from second, third, fourth hand accounts, and most of the oldest manuscripts that mention him only go back to about 1000 AD or so, if memory serves. So there's actually a very interesting story to tell about how we piece together our knowledge of history as a scientific process, but that's a topic for another day. Anyway, about 100 years or so after Anaxagoras, Aristotle came along and accepted most of what Anaxagoras said and made one very important correction, which was that the Earth is in fact round. And he argued that the evidence for this is that if the travelers going south see different stars than you do up in the north, and the shadow of the Earth is on the moon is round. And very interesting quote from Aristotle's writings, which we have better records of than most of his contemporaries, because he's the one who established the received wisdom of Western knowledge for about 2,000 years, and so his writings were preserved better than anybody else's. Every portion of the Earth tends towards the center until by compression and convergence they form a sphere. That's what he wrote, and that is should be a very familiar concept to modern audiences. He's essentially discovered gravity, although he doesn't realize. Neither Aristotle nor any of his contemporaries for 2,000 years realized that that's what he'd figured out, gravity. But he was a geocentrist. He thought that the Earth was the center of the universe. So he got that wrong, and that mistake stuck with us for 2,000 years, which is not to say that nobody figured it out earlier. About 100 years or so after Aristotle, a fellow named Aristarchus was the first to advance the theory that the sun and not the Earth is the center of the universe. He was also the first one to to estimate the distance of the sun. He was wrong by a factor of 20, but he was correct. He was correct in that he established that the sun is much, much further away from the Earth than the moon is, which is an important thing to know, and I'll get to why in a second. But it's interesting to know how he measured this distance. What he did was he waited until the moon was half full, and because he knew that the light of the moon came from the sun, he reasoned that that when the moon is half full, that the angle from the Earth to the moon to the sun must be a right angle. And so if you measured this angle here, which is to say the angle between the line of sight to the moon and the line of sight to the sun, you could get the geometry of this triangle and figure out what this distance is. And he measured this angle at 87 degrees. And in fact, the correct number is about 89, because he didn't have very good instruments. And that's why it was off by a factor of 20, because when this angle is big, a very small error in this measurement will give you a very big error in this measurement. But again, close enough to tell you what's important, which is that the sun is very far away. And the reason that's important is because another important question at the time is the Earth flat? And Aristotle advanced some evidence that it was round, but if it's round, it's important. The obvious next question is, well, how big is it? And that was figured out by a fellow named Eratosthenes about yet 100 years later. He measured the angle of a shadow cast by a vertical stick in Alexandria, Egypt, during the spring equinox, when the sun is directly overhead in Syene, Egypt. And based on that angle, he was able to work out the radius of the Earth, and came very close to the right answer. Now, Carl Sagan, the famous and venerable Carl Sagan, wrote a book called Cosmos, where he tells this story. And when he tells this story, he says the only possible reason that a pole in Alexandria could cast a shadow while a pole in Syene does not is that the Earth is round. And that turns out not to be true. There is another possible explanation for that. And that is, if the sun is very close to the Earth, you can have a flat Earth where you have the sun directly overhead in Syene, but not overhead in Alexandria. But that's only possible if the sun is very close. And that's the reason it's important to know how far away the sun is, and that's the reason that Aristarchus' measurement of the sun, even though it was too small by a factor of 20, established that the sun was far enough away that Eratosthenes' measurement of the size of the Earth was reasonably accurate. So, ever since 300 BC, not only have we known the Earth is round, we've known how big it is. So all these flat earthers are, their information is out of date by over 2,000 years. Just as a little side note, so this question of how far away is the sun wasn't really answered accurately until 1769. Aristarchus, as I mentioned, got the answer too small by a factor of 20. But that was the accepted value for about 1900 years until Christian Huygens in 1653 got the right answer by pure luck. If you go back and look at the method by which he did his calculations, it was completely bogus. And basically it was based on a guess that Venus is the same size as the Earth, which he had no basis for knowing, but which turns out to be true. So he just got incredibly lucky that he guessed that it was the same size and got it right. The first really correct answer based on actual evidence available at the time was in 1672 by Giovanni Cassini, and then James Cook got the first really good measurement in 1769. So all that's fairly recent by historical standards. But back to the main narrative of the story, 100 years after, I'm losing track of all these Greek names now, Eratosthenes, yeah, thank you, a fellow named Hipparchus comes along and invents trigonometry, which gives him the mathematical tools to start making much more accurate measurements and predictions and mathematically sound theories. He wrote 14 books. So I could give a separate lecture just on Hipparchus and all the clever things that he figured out, and all the instruments that he invented. It makes a really fascinating topic, but we don't have anywhere near enough time for that. The point is that by about 100 BC, our understanding of the cosmos, or at least the solar system, was pretty good empirically. It was good enough that we were able to make very accurate predictions of the movements of the planets, predict eclipses, predict the seasons, and we even built computers that did all these laborious computations. This is a photograph of something called the Antikythera mechanism, which is named after the place where it was found, the Greek island called Antikythera. It was underwater, which is the reason it's corroded, but they've used X-rays to figure out its internal structure and reverse engineered it to figure out that this is actually an early computer made out of gears whose purpose was to predict the movements of the planets. The Greek understanding of cosmology reached its zenith with a fellow named Ptolemy, who lived between 100 and 170 AD, Common Era, after Christ. He tackled this, what was still an enduring mystery of why Mars sometimes seems to move backwards, the retrograde motion of Mars. So Mars mostly moves from west to east, along with all the other planets, but every now and then does this little loop back before continuing east. And the reason it does that, we know today, of course, is that Earth and Mars both orbit the sun, and Mars is further away, and things that are further away move more slowly. So the Earth will catch up and overtake Mars once every 2 years, which is the reason why the window of opportunity to launch spacecraft to Mars only happens once every 2 years. And during this period, while we're overtaking, the parallax causes Mars to appear to move in the other direction. But Ptolemy had a different theory. He followed Aristotle in his belief that the Earth was the center of the universe, and also that the heavens were pure and divine and perfect, and because they were perfect, the things in the heavens had to move in circles, because circles were the most perfect geometric forms. And so he came up with a theory called epicycles, because you can't actually fit a circle to the observations, because planets, in fact, do not move in circles. So if you try to figure out what the circular path is, you will fail, because it isn't circular. So his theory was that, well, the planets move in a big circle, but then they have a little mini circle kind of superimposed on top of that. And you can have epicycles on top of epicycles, so you have something moving around the Earth with an epicycle that then has another third epicycle, and all of this was worked out in painstaking detail. And the theory worked. It actually allowed Ptolemy to make the most accurate predictions of planetary motions to that time. But of course, it's not because the theory is correct. It's because it turns out that if you add enough circles, you can make any kind of a path. Whoops. So here's just a little example of that. This is 40 epicycles, and so that's what they look like. And now this is going to draw out the path that this set of epicycles predicts. And the reason that you can do this is because of something called Fourier analysis, which wasn't discovered until the 18th or 19th century, I forget exactly when. But it turns out that you can take any function and decompose it into circles, essentially. As long as you have enough of them. But of course, Ptolemy didn't know this. So he'd almost, if he'd thought about it a little bit more, he might have figured out Fourier analysis, and again, advanced the cause of science, and speeded up our development by 2,000 years. But he didn't. And then Rome fell, and the Catholic Church took over, and we had the Dark Ages. And other than in the Arabic world, where they were still making progress mainly in mathematics, in the Western world from the death of Ptolemy up until 1543, quite literally absolutely nothing happened. No scientific developments of any kind. And you can see these wonderful maps that were done even till very late in this period. This one is from 1539. Here's a really beautiful color one from 1568. So after the New World is discovered, and you can see that there's a fairly accurate map of the Earth here, but it's still depicted as the center of the universe with everything else going around it in Ptolemaic epicycles. And that was, again, the received wisdom until 1543. And what happened in 1543 was a fellow named Nicolaus Copernicus died. And the reason that his death was important was because before he died, he wrote this book, laying forth an argument that the Earth was not the center of the universe, that the sun was in fact the center of the universe. Essentially recapitulating, not Aristarchus, but the guy before him, the Greek argument. He rediscovered that and decided that it was true and wrote this book to defend it, but he was so terrified of challenging the conventional wisdom, which to that point had been part of Western society for 2,000 years. He was so afraid of challenging that and challenging the power of the Catholic Church that he would not allow this to be published until after his death. So after he died, it was published, and that set off the modern era, which this is a quick overview of that. Starts with Copernicus, it goes through Galileo and Newton and a couple of other people, and again, the details here aren't that important. The main reason I put this up is to highlight the fact that individual human lifetimes are now occupy significant chunks of this period of time. And so everything now is happening over the same time span as before, but we now have a lot more players and things are going to happen a lot faster. And another important development during this time is that the telescope was invented, which that would make another interesting talk just in and of itself, the development of the technology that went along with these scientific advancements. But again, no time for that here. The next interesting historical development was Galileo, who read Copernicus's book and decided that it was right, and also got himself a telescope. And now telescopes have been around for a while, but what Galileo did that was revolutionary is he used his telescope to look at the sky. He was the first one to do that, which was a revolutionary thing to do at the time because nobody thought that there was any point in using telescopes to look at the sky because they didn't think there would be anything interesting to see there. If you just point a telescope at a star, it still just looks like a star. And so until Galileo, nobody paid much attention to telescope, to what you could see in the sky through a telescope. But Galileo did, and one of the things that he discovered is that when you look at Jupiter, you see two interesting things. The first thing you see is that it's not a dot. You can actually see that it's a circle, that it has a size. And you also see these four other things that look like very bright stars that are right next to it, and that stay next to it as Jupiter moves across the sky. They move around Jupiter, but they don't move away from it. These are, of course, the four Galilean moons of Jupiter. And Galileo realized correctly that Jupiter is its own little, that these were moons, and that they're moving around Jupiter, and that this is further evidence that the Earth, that Copernicus was correct, and the sun is the center of the Earth, and is the center of the universe and not the Earth. Another thing that he observed is the phases of Venus. So if you look at Venus through a telescope, you can again see that it's a disk and not a point, and you can see that it has phases just like the moon does, and that it changes in size from different times of the year. So Galileo also, of course, famously wrote a book defending this idea, which was then squashed by the Catholic Church. Again, another interesting story, which I don't have time for. He sparked a sort of a craze of astronomical observations. And the most famous of the astronomical observers, the people who just started pointing telescopes at the sky and making measurements that were much more accurate than any that had ever been done before, was a fellow named Tycho Brahe. I'm not sure exactly how it's pronounced. Does anybody know?
Tycho Brahe.
Tycho Brahe, thank you. Tycho is interesting. It's not evident in this picture, but he lost his nose in a fight and had a false brass nose. So some pictures that you'll see of him highlight that aspect of his physical appearance. But he collected vast catalogs of astronomical observations. He just would measure the positions of the planets and the sun and the moon in the sky and write it all down. Using instruments kind of like this. This is a reproduction of one of Brahe's instruments. It's a little hard to tell the scale, but this thing is huge. It's about, I would guess, 2 stories tall. A person would stand about this high next to it. All that data was number crunched, manually of course, by a fellow named Johannes Kepler, who boiled it all down to Kepler's famous 3 laws of motion. He figured out that all of Brahe's data and all the other data that was being collected by other people, but mainly Brahe, could be accounted for by 3 laws. First of all, planets do not move in circles, they move in ellipses. That there is a relationship between the speed at which the planet moves and the distance. And the further away it is, the slower it moves. He didn't put it quite that way, he put it much more precisely than I'm telling you. And there's a third one that I've forgotten now.
Equal areas and equal times. It carves out equal.
Right, equal areas and equal times. Again, the details don't matter. What matters is that Kepler was the first one to really get the math right of exactly how the planets move. They really do move in ellipses, and he got the time right, and so his math was able to make the predictions with the same accuracy or better than Ptolemy, but his math was much simpler because it was correct. But he still didn't have a theory of why all this was happening. He didn't know why planets moved in ellipses. He just knew that they moved in ellipses. And by the way, Kepler, this is an example of the technological advances that were happening at the time. This is a drawing of, excuse me, of one of Kepler's telescopes that he invented. And again, notice the scale, the people down here give you an idea of how huge this thing is. A little digression here in the history of discovery. This is not going to seem relevant, but trust me, it will come back into play later. In 1676, a Dutchman named Ole Römer was the first to measure the speed of light, and he did it by timing the eclipses of the moons of Jupiter and figuring out how they diverged from the predictions made by Kepler at different times of the year, and reasoning that the timing differences were due to the amount of time that it takes the light to get from Jupiter to the Earth. Backsolve that to get a pretty good estimate for the speed of light. The point here is that from about the mid-1600s on, the speed of light is known. So then again, in the mid-1600s, we get the granddaddy of all scientists, Isaac Newton. Again, could do a whole talk, could do a whole series of talks, could write volumes just about Newton, because he is arguably the greatest scientist of all time, and spanned an incredible range. He did not just astronomy, but all kinds of other branches of physics he laid the foundations for. This picture here is of Newton doing some experiments with light, which is, again, a whole other series of talks. But the interesting thing here is in the background, standing on this table, is one of Newton's telescopes, which looked like this. This one's a reproduction of that telescope. He invented this whole new kind of telescope that used mirrors instead of lenses. Up until that point, telescopes were made out of lenses, and Newton figured out how to make them out of mirrors. And the reason that's important is because it's easier to make a mirror really big than it is to make a lens really big. And so that was an important technological advance. But in the history of astronomy and cosmology, of course, and science in general, what Newton is mainly known for is this book, Philosophiae Naturalis Principia Mathematica, where he, for the first time, figures out that the reason that planets move in ellipses is because of gravity. and that gravity is a force that emanates from all bodies and dies off as the inverse of the square of the distance, and that with this simple fact, you can account for everything that we see, everything that could be seen in the cosmos with the instruments available at the time. You could account for Kepler's laws. And this was really revolutionary in the history of human thought, because it was the first time that the physics of the heavens and the physics of the earth had been unified. Up until then, it was believed, and by the way, Newton believed this too, because Newton was a deeply religious man, ironically, that what was going on up in the heavens was completely different from what was going on here on Earth. And Newton's theory of gravity shows that that's not true. It's exactly the same up there as it is down here. Yeah, question?
Hold on a second.
You've been saying that the sun is the center of the universe. Did Newton figure out that that wasn't true, or if not, who figured that out?
Well, okay, so at that point, the universe was the solar system. The telescopes at that point were not yet powerful enough to resolve enough, to get enough data about stars to figure out that we're actually in a galaxy and that the Magellanic Clouds are galaxies. That data wasn't yet available. So when I say the universe, up until this point, and in fact, up until, I think about the 1930s, but I'll get to that. The universe and the solar system are synonymous, because up until that point, we just didn't know that there was anything beyond our solar system, other than stars, of course. But we didn't know that the stars differentiated themselves into galaxies and so on and so forth. Anyway, so interestingly, Newton didn't believe in gravity. He figured all this out, but in a letter he actually wrote, "It is inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact." In other words, this gravity thing is kind of magic, because here you got the Earth down here, and the moon, 180, I forget how many thousand, hundreds of thousands of miles away, and the sun millions of miles away, and they're all pulling on each other. But from our experience here on Earth, you can't pull on something unless it's attached to like a rope or something. I mean, the only way that you can pull or push on something is if you're in physical contact with it. Anything else would be magic. If I could pull on that thing and draw it closer to me without anything material in between us, that would be magic. And so gravity was a kind of magic, and Newton ironically didn't believe in magic. He believed in God, but he believed that God created the universe to operate according to natural laws, and that the goal of science was to discover God's laws, but that they would be lawful, that God's laws would make sense in some way, and gravity was force operating at a distance didn't make sense to him, and he never accepted it. Nonetheless, his theory was, again, correct and therefore accepted, and led to a tremendous number of advances, along with technological advances, led this fellow named William Herschel in 1781. Is that right? I got a little covering up thing. Yeah. Using a telescope that looked kind of like this. This is a 49-inch Newtonian reflector. So 49 inches. The mirror is this big, huge. Using that, he was able to discover the first new planet since antiquity. He discovered Uranus using this telescope. And so for the first time since the dawn of man, we knew of more than 5 planets, plus our own. That was followed very quickly, relatively speaking, by the discovery of Neptune in I give a range of dates here because the way that Neptune was discovered was not the same way that Uranus was discovered. Uranus was discovered because he was making measurements with his telescope and he saw the star that moved. And so he realized it must be a planet. Neptune was discovered when they tracked the orbit of Uranus and realized that it didn't obey exactly the predictions that Newtonian mechanics predicted for it. And so there must be something else out there pulling on it. And again, they back-solved it to figure out where this something must be. And then they looked at that location and there was Neptune. And that process took about 20 years and was done by these two Frenchmen, Alexis Bouvard and Urbain de Leverrier. I'm probably butchering their pronunciations. Leverrier also was the first one to notice that Mercury actually does not quite move in an ellipse. So there's this little anomaly in the orbit of Mercury where the perihelion, the point of the ellipse that's furthest from the Sun, moves around a little bit. It's called precession. This diagram exaggerates the effect dramatically. But this was a big mystery in its day because all the other planets moved, as far as anybody could tell, as far as the measurements of the day could tell, in perfect ellipses that didn't precess. But Mercury precessed, and people were trying to figure out why. One of the possibilities was that there was another planet that they called Vulcan that was pulling on Mercury in exactly the same way that Neptune was pulling on Uranus. But of course, there is no... They looked where it should be and they didn't find anything, so that was still a mystery. Now here again, I have to make a little divergence, a little digression in the story and go back to ancient Greece and talk about Euclid, who was the first to formally codify geometry. And one of the, has anyone here not heard this story about Euclid's fifth postulate? Wasn't told about it in their elementary school geometry class?
What?
Okay. All right. How many here have never taken a geometry class? Okay, I'll go back to basics then. So Euclid figured out geometry based on 5 assumptions, the first 4 of which sound very simple and obvious and almost impossible to argue with. They're things like, between any 2 points you can draw one straight line. Pretty uncontroversial. His 5th assumption was, if you have a line and a point not on that line, you can draw exactly one line through that point that's parallel to the original line, which also seems kind of intuitively obvious. But saying that is a mouthful. And it turns out there are lots of different ways that you can say the same thing, and they're all long and complicated and cumbersome, and this was considered a blemish on Euclid's theory for 2,000 years. For 2,000 years, mathematicians tried to come up either with a simpler way of saying it or to prove that it was true from the other 4 postulates or assumptions that he had made. And they failed. And the reason that they failed is because it turns out that his 5th postulate is not true in the same sense that the first 4 are. It's an assumption that you can either make or not as you choose, and if you make a different assumption, if you assume, for example, that you can draw multiple parallel lines through a point, then what you end up with is a new kind of geometry that today we call non-Euclidean geometry. You're basically describing the geometry of curved surfaces. So if you assume that you can draw multiple parallel lines, you end up with geometries that look kind of like this, is saddle shapes called hyperbolic geometries. And if you assume that you can draw no parallel lines, you end up with the geometry of the surface of a sphere. But it took 2,000 years and a lot of intellectual pain for people to realize this. This would make a chapter, this story would make a good installment of the series in and of itself. So keep that in the back of your mind as we go into the next episode, which is in the mid-1800s, a Scottish scientist named James Clerk Maxwell did for electrodynamics, the theory of electricity and magnetism, what Kepler had done for planetary orbits. He condensed all of the knowledge that was available about the behavior of electricity and magnetism in the day down to 4 simple, relatively simple equations. Those are them. He was 34 when he did this, so that's why I have two pictures of him, because when he did this work, he looked like the picture on the left, even though most of the pictures that you'll see of him if you search online are more like the one on the right. These mathematical equations make an interesting prediction. They predict, if you solve them, the solution predicts that you will get a wave, that if you take an electric charge and shake it, the result will be a wave of electricity and magnetism that propagates through space at a particular speed. And that particular speed turns out to be exactly the same as the already then known speed of light. And so it was hypothesized that light was actually an that this was an indication that light is actually an electromagnetic wave, which turned out to be true and turned out to be confirmed by subsequent experiments. But it introduced a mystery, which is all other waves that are known, so for example the sound waves that are traveling through the air, all other waves require some kind of a medium in order to propagate through. And so these electromagnetic waves must also have some kind of a medium, and this medium was they just gave it a name. They didn't know what it was, but they called it the luminiferous ether. And an effort was begun to try to detect and find the luminiferous ether, which culminated in an experiment in 1887 done by Michelson and Morley. This is an actual photograph of their experimental setup, to try to measure the speed of the Earth through this hypothetical ether. So it was, they set up, essentially, this thing is called an interferometer. I'm not going to go into the details of how it works, but basically it measures the speed of light to extreme accuracy. And they set this up on a very stable platform. This is a block of granite that's floating in a donut-shaped pool of mercury. And they let it sit there for a year to try and detect the change in the speed of light relative to this hypothetical ether as the Earth moves around the sun. So the idea is that as the Earth moves around the sun, it's moving in different directions at different times of the year. And so the speed of light relative to the ether you should be able to measure that difference. Because you know how fast light moves, you know how fast the Earth moves, and so you know what the relative change in the speed should be. And there's a pretty good argument that this instrument should have been sensitive enough to detect it. But they didn't detect it. And this led to a lot of head scratching. Because how could this be? How is it possible that the speed of light is the same in all directions? And that puzzle, of course, was solved by this guy, who you've probably heard of, with his theory of relativity. He just said, let's just assume that the speed of light is in fact the same for all possible observers, that this is a fundamental constant of nature, and work out the consequences of that. And the consequences of that turn out to be all these really weird, non-intuitive things, all of which turn out to be true, like that when you move fast, time slows down. That was the special theory of relativity, his first take at it, which was published in 1905. And then 10 years later, in 1915, he generalized that theory to gravitational fields and figured out that Newton was actually right, that gravity is not this mysterious force that operates at a distance, that what's really happening is that the geometry of space-time is non-Euclidean, which is to say, space-time is curved. And I once was fortunate enough to see a lecture by Kip Thorne, who is one of the preeminent physicists of general relativity theory down at Caltech. And he opened his talk, he took out a basketball, which I forgot to bring with me. I'll use this eraser instead. And he threw it into the air and said, it looks as if this basketball, is moving in a curved path, but in fact it's moving in a straight line through curved space-time. And that quote just stuck with me. Because what is a straight line? A straight line is the path on which an object will get to wherever it's going with the least amount of energy expended. And that is that path that you just saw, which looks like a parabola from our perspective. But the reason is because what's really going on is not that gravity is pulling you down, but that the surface of the Earth is accelerating you up. Again, a whole nother talk. Really complicated, hairy math, really non-intuitive results, like if you're in a very strong gravitational field, again, time slows down because what's really going on is you're being accelerated, which means you're moving faster and faster and faster, which means the time slows down. It all gets really weird. I don't have time to explain it all in this talk. But it made a prediction about the deflection of starlight around the sun that differed from Newton. So Newton's theory actually predicts that starlight will be deflected by a gravitational field, and the general theory of relativity agreed with that, but said that Newton got the amount wrong by a factor of 2. And in 1920, so 5 years after the theory was published, Arthur Eddington did the first measurement to test this. And the result of his experiment, he measured the deflection of a star, a known star, around the sun during a total eclipse. This is the actual photograph that Eddington took, the actual photographic plate that proved that the theory of general relativity was correct. And this is the thing that launched Einstein into international stardom. So when this was announced, all of a sudden Einstein became famous and synonymous with genius. Yes, question in the back.
There wasn't, hold on a second.
So if Einstein wasn't right, then would it be more symmetrical?
So the
fact it wasn't symmetrical, was that what told you Einstein was right?
No, I don't think you can actually see it on here. This is really just a picture of it. All you can see here is a picture of the total eclipse, and it's a negative. It's a picture of the original plate. The negative. This photograph was made on a glass plate, and so it's a negative. And so the dark parts are actually bright. What you're looking at is the sun's corona. And the actual star that Eddington is measuring is a little tiny dot in there somewhere. I'm not sure exactly where it is. It's very close to the surface of the sun. And I don't actually see it, but it's in there somewhere.
Can I ask you a question?
Yeah?
How many more slides do you have? A lot of them?
No, we're nearing the end.
Okay, because otherwise you hold the questions until the end.
Okay. Yeah, we're getting close to the end. Anyway, so science is now converging very rapidly on some fundamental truths, but there was a pretty significant problem. So this is, where'd my cursor go? This is general relativity in a nutshell. This is Einstein's field equation for gravity, and kind of like Maxwell's equations predicted these electromagnetic waves that turned out to be true, this equation predicts that the universe cannot be static. It has to be either expanding or collapsing, but it can't be standing still. And this bothered Einstein because he thought that the universe was static. And so he just, out of his thin air, decided to add this term to the equation that he called the cosmological constant in order to make things balance out so that the universe could be static. But of course the universe is expanding. So Einstein passed up on the opportunity to make one of what could have been one of the greatest scientific predictions of all time, because about 20 years later, Edwin Hubble, using this telescope up on Mount Wilson in Southern California, you can actually go down there and still see this telescope, still there, discovered that the universe is in fact expanding by looking at gravitational redshifts of stars and seeing that the ones that are further away have a larger redshift. So when Einstein learned of this, he called the cosmological constant his greatest blunder, which is ironic for a reason that we'll get to in about 30 seconds. Anyway, once you realize that the universe is expanding, then it's a natural thing to do to try to figure out, well, how did it get to be that way? So, well, if it's expanding now, then it must have been smaller in the past than it is now. And if you work the math, you discover that, yeah, the universe was smaller. In fact, it was once very small. And in fact, so small that the universe must have arisen from some giant cataclysm, which was dubbed the Big Bang. interesting story. The Big Bang was actually, the term the Big Bang was coined by, I forget who it was now, was coined by a scientist who was trying to deride the theory as ridiculous. But of course it turns out to be correct. And one of the things that this theory predicted is that you should be able to see the remnants of the Big Bang all around as this field of background radiation at a certain frequency. And that was confirmed by these two gentlemen, Robert Wilson and Arno Penzias, in using this antenna. And somewhere on there is the date, and it was in the late 60s or early 70s that they did this, so I didn't write the date down. Anyway, this photo is blurry because it's a screenshot from a video. These two guys are still alive. You can actually go talk to them. This is what they looked like in the mid-70s when they did this interview. So we're getting now into very contemporary, recent occurrences. So the cosmic microwave background radiation, as it's called, which is the evidence for the Big Bang, was recently mapped out with incredible accuracy by this spacecraft called COBE, the Cosmic Background Explorer. And it was discovered that it was not uniform, that it had irregularities in it. And by doing very careful analysis of those irregularities, they were able to trace the history of the universe back to an incredibly short time period after the beginning, whatever that was. Some tiny fraction of a second, they've actually been able to trace this back. And they've also been able to, based on this data, get an incredibly accurate estimate of the age of the universe. And I think this gentleman just brought to my attention that the estimate here, 13.77 billion years, was updated recently to 13.8 billion. But they're making very tiny corrections now. This is a pretty accurate number. So we got a pretty good grip on what's going on, except there are still some mysteries that science is trying to explain. You may have heard of dark matter and dark energy, which we still don't know. Dark matter was actually discovered in 1922 by this guy, Johannes Kepler. The evidence for it now is pretty incontrovertible. If you look at the way galaxies rotate, and we can get very accurate estimates of the mass of the visible matter, and there's just not enough of it to account for the movement of the stars. So there must be something else exerting a gravitational field inside these galaxies that we can't see. And we have no idea what it is. Still trying to figure that out. Dark energy was discovered in 1990, just at the turn of this century. When I was coming of age, the turn of the century always meant the turn of the 19th century into the 20th century, but that's no longer the case. Using this instrument called the Chandra X-ray Observatory, this is actually a telescope that was launched into space. This down here, this is the mirror and the mount for the mirror for this incredible instrument. This instrument was used to make the most accurate readings of X-ray emissions of distant objects. And using that data, they were able to determine that not only is the universe's expansion not slowing down, as you would expect if everything is being held together by gravity, but it's actually speeding up. So there's something causing this expansion to accelerate. And it's called dark energy, which is just a fancy way of saying something that we have absolutely no clue what it is. But ironically, it can be accounted for by Einstein's cosmological constant. So Einstein got it wrong twice in both directions, which is one of the great ironies of scientific history. So just a couple of other things that are going on today. You may have heard of gravitational waves, which are being measured by this instrument called LIGO. This is essentially the same thing as the Michelson-Morley experiment, that experiment that was on the concrete slab, except made much bigger. The arms of the interferometer here are, where's my pointer? These things, these are these giant pipes that are pumped down to a vacuum. I think they're about a mile or so long. Half a mile? Did somebody say half a mile?
Yes.
Okay, half a mile long, thank you. At the ends are these mirrors these incredibly huge mirrors, they're about this big. They're mounted on these intricate mounting points to make them absolutely motionless because they're measuring movements of these mirrors that are smaller than an atom. And so they have to be isolated from all the vibrations. When a truck drives by this setup, they can measure it. This is a photograph of the mirror assembly. Again, unfortunate there's not a person standing next to it for scale. It's about 6 feet from top to bottom. It's huge. This is just some of the data. This is what a gravitational wave looks like when you measure it. This is the evidence, the first direct evidence that we have that another prediction of general relativity, namely that neutron stars and black holes occasionally collide and coalesce into each other, are true. And the details of these little wiggles are exactly what general relativity predicts. We've discovered planets around other stars using this instrument, the Kepler Space Telescope. They actually, the first exoplanets were discovered using ground-based telescopes, but as of mid-March of last year, Kepler has discovered 2,342 planets around other stars. And there's data to hint at the existence of about 2,200 others. And the total number of exoplanets that have been discovered to date is to March of last year, 3,706. So planets around other stars are old news now. I want to just close, this is a little bit out of order, with the Hubble Space Telescope, which took what I think is one of the greatest photographs in the history of human endeavors of any kind. They pointed it at this little piece of the sky here, and the moon over here is to scale, to give you an idea of how tiny this little patch of sky is. They picked this because it was a patch of sky that had, as far as they knew, no stars in it. And they set up the shutter to do a time exposure 22 days long. And I'm sure you've all seen this. This was the result. Every spot of light, even the tiniest spot of light in there, is a galaxy. In that tiny little spot. That's the universe that we live in. And you can see it with your own eyes. And you can see the moons of Jupiter directly with your own eyes with a pair of binoculars. And it's an exercise I think anybody who wants to live a rational life should do. They should actually do some of these experiments for yourself. Get yourself a telescope and check. See if the things that I've told you are actually true. Don't take my word for it. Do the experiment. And that's all I got.
Okay, wow. A great talk. So I'm going to try and walk the mic around and remember, okay, he's going to turn the lights on. And remember that hold the microphone close to your mouth. Do you understand? Close to your mouth. Otherwise, it'll start feeding back. I'll go around the room. And should we give about 10 minutes?
Yeah, sorry I ran long, but there's a lot of material here, and I get really excited about it.
I got a little mathematical anomaly.
Yep.
Kepler's third law equates a cube of something to a square of something, and that's an analog. There also is a mathematical identity because you have two different dimensions, cubes and squares. There's a digital equivalent of that, which is the difference of two integers. You're talking about integers. The difference of the cube of two integers equal to the square of a bee. A beehive has the hexagon connections. Okay, if you look at the hexagon, you can go around and around and count the number as you go out of in hexagons. So they have equivalent of cubes of difference of the hexagons of a beehive.
Okay, I have to take your word for it. You are way beyond the limits of my knowledge here.
Okay.
I've always been perplexed by several aspects of gravity. First, how in the world does mass bend space? Second, if gravity is only a curvature of space, why are they looking for gravitons?
Very good questions. Why does mass bend space? We don't know. We just know that it does. Why it does is still a great mystery. One that may never be solved. We may just have to accept that this is how the world works and that we'll never have an explanation for it. Or somebody might come up with a brilliant idea that will explain it, but at this point, nobody has a clue. Why are they looking for gravitons? The reason they're looking for gravitons is because there are, in addition to general relativity, there is another scientific theory which explains the other half of our existence, which is to say that there are, what goes on here on Earth are material selves. This is quantum mechanics, which describes basically everything that happens other than the really big stuff, other than gravity, is all accounted for by quantum mechanics, which again, I could do a whole talk on that. We know that either quantum mechanics or general relativity has to be wrong. And the reason we know this is because they're incompatible with each other. If you push the theory of relativity down to the very small, it falls apart. And if you try to pull the quantum theory up to the very large, it falls apart. And they start to disagree with each other somewhere in between. But so far, all the experiments that we've been able to do have agreed perfectly with both of these theories. We've not been able to get to the realm where they disagree, because in order to do that, you basically need to be near the surface of a black hole, and that's really hard to recreate in a laboratory. But there's this quest to unify these two and figure out where the problem is, because it's known that there must be a problem somewhere. And one of the strategies that's been used to try to unify these theories is to try to turn general relativity into a quantum theory. And one way to do that is to assume that there is a particle that mediates the gravitational force in the same way that there are particles that mediate all the forces in an atom and among atoms. So far that's not been successful. But that's the reason they're looking, because if you could find experimental evidence for gravitons, that would be evidence that, yes, in fact, there is something quantum going on in general relativity, and that they're on the right track trying to pursue that. Yep.
Yes. What causes the path of Mercury to not be the same?
Another excellent question. I'm not sure I know the answer in detail, but the reason that it's only Mercury is because Mercury is the only planet that's close enough to the Sun so that the gravitational field at that point is strong enough that the difference between the predictions made by general relativity and the predictions made by Newton start to diverge. And even there, the difference is tiny. You need very accurate observations in order to be able to detect it, which is why it wasn't detected until the mid-1900s.
Are you familiar with the research that was done recently, I think culminating in 2014 at the South Pole with the South Pole telescope or something there related to the polarization of the cosmic microwave background and how that somehow clarified the Big Bang?
No. Sorry.
So going back to what you said about flat earthers, that they exist. Because Earth is further away from the Sun than two planets and closer to the Sun than all the other planets, we should see two planets have a new phase. You mentioned the phases of Venus, right? So Venus, since it's closer to the Sun, we should see a new phase of Venus. And all the other planets that are further away, we wouldn't see a new phase. Is that what we see? And isn't that undeniable proof that those planets are closer to the Sun than we are and the other planets are further?
So the answer to your question is yes, but you are radically misunderstanding the mindset of flat earthers and other like-minded conspiracy theorists. That kind of argument is not going to persuade them because there are so many more slam dunk arguments against the flat earth. The interesting thing about the flat earth, it's not really an argument about whether the earth is flat or not. It's an argument about how big it is, because flat is just a special case where the radius is infinite. So how can you tell the difference between a truly infinite radius and one that's just really, really, really big? I mean, we know what the radius of the Earth is. It's 8,000 miles or whatever it is. And there's just no arguing about that. And they're not arguing about it because they really believe that they have good data. They're arguing about it because they're conspiracy theorists, and they don't trust authority, and they're lazy, and they don't want to do their homework, and they want to feel like they're part of a special club, and they have inside knowledge. And so you're never going to persuade them. There was a question up here.
Okay, this will be the last question. No more questions. Otherwise, you can always talk to the speaker at the speaker's table. Please keep it short.
You know, it's interesting that all these great discoveries are made by individuals, not committees.
Now, that used to be true. That's not true anymore.
Well, yes.
Nowadays, science has turned into very much a team sport.
Well, now, why would you want to populate another planet with the most dangerous animal on Earth?
Okay, I'm going to have to defer that question to society at large, because that's not really my place to answer. I can give you my personal opinion, but I'll do that off the air.
Okay, thank you, Ron.